Welcome to the deep dive. Today we're heading out to Jupiter, looking at its amazing auroras through, well, the eyes of the James Webb Space Telescope. If you're keen on understanding the big science discoveries, getting right to the heart of it without, wading through dense papers, this is for you. Think of it as your shortcut to some really cool new findings.
Exactly.
Yeah.
We all know Earth's auroras, the northern and southern lights.
Yeah.
Beautiful, right? Solar particles, magnetic fields, atmosphere. Astronauts even see them swirling below the space station.
Right, we have a good picture of that. But Jupiter, it's on a whole other level. We're talking auroras that are hundreds of times brighter. And the latest from Webb is, well, it's pretty startling, not just a glow, but something much more dynamic, flickering even.
And that's our focus for this deep dive. We want to understand first why they're so intense on Jupiter, and second, what these brand new Webb observations are telling us about how they behave these rapid changes, and honestly some new mysteries too. We've got some great source excerpts detailing all this.
Okay, let's start with that scale. Hundreds of times brighter. That's just immense. It really speaks to the sheer power involved, doesn't it?
It really does. And a key difference from Earth is where the particles come from. For us, it's mostly the sun. But Jupiter, it has this major internal source. It's moon Io.
Ah, Io. The volcanic one.
The intensely volcanic one, yes. It's constantly chucking material sulfur, oxygen out into space. This stuff forms a sort of donut, a plasma torus, around Jupiter.
So Jupiter's getting hit by solar wind, and it's constantly supplied with particles from its own moon. That's a big deal.
It's a fundamental difference. And Jupiter's magnetic field is, well, it's enormous. A giant cosmic net. It scoops up particles from the sun and from Io, and then it acts like a giant accelerator, whipping up to incredible energies.
And that's what creates the super bright auroras when those particles slam into the atmosphere near the poles.
Precisely, which leads us nicely to Webb.
Right. The James Webb Space Telescope. It took a look, a really detailed look, with its near-infrared camera NIRCam back on Christmas Day 2023. Why infrared, though? What does that give us?
Good question. Infrared light lets us see different things than visible light. It can pierce through some of the atmospheric haze, for one. It also lets us see specific molecular signatures, like the one they focused on here. So NIRCam could get this incredibly high-resolution data revealing structures and changes we just couldn't see before.
And those changes were the big surprise, weren't they? I remember reading the phrase cosmic fireworks. That sounds active.
Very active. Jonathan Nichols, one of the researchers, apparently said, what a Christmas present it was. It just blew me away. See, the expectation was, maybe things would brighten or fade over, say, a quarter of an hour, 15 minutes or so.
Kind of a slow, majestic shift.
That was the idea. But instead, they saw parts of the aurora just fizzing and popping with light, as he put it. Brightness changes happening sometimes within seconds. That rapid flickering was totally unexpected.
Wow, seconds? So much faster than anyone thought. What exactly were they measuring that showed this flickering?
They were looking at emissions from a specific molecule called a trihydrogen cation, H3+ flaclo. It gets created in the aurora. The light it gives off tells you about the energy hitting the atmosphere. And the key finding was that this H3+ light was varying, changing intensity way, way faster than predicted.
So this H3+ flickering isn't just a visual thing. It's a direct measure of energy rapidly dumping into Jupiter's upper atmosphere. It tells us about heating and cooling.
Exactly. It's a tracer for these really dynamic energy inputs. And it gets even more fascinating because they weren't just using Webb.
Ah, the Hubble part of the story. They looked at the same time with Hubble.
That's right. Simultaneous observations. Webb and infrared. Hubble and ultraviolet. You'd normally expect, a bright spot in one to correspond to a bright spot in the other. Just different wavelengths showing the same energetic event.
Makes sense, like seeing heat and light from the same fire.
You'd think. But, and this is the really bizarre part, the very brightest areas Webb saw in the infrared, they just weren't there in Hubble's ultraviolet pictures. No corresponding bright spot.
Okay, that is weird. Bright in infrared heat, but dark in ultraviolet light. How does that even work? That's a real head-scratcher.
It is. The current thinking, the best explanation they have right now, points towards needing a huge number of particles hitting the atmosphere, but particles with very low energy. And that itself is puzzling because models didn't really predict you could get that many low-energy particles concentrated enough to produce such a bright infrared signal as seen by Webb. It sort of seemed impossible before.
So the observations are forcing a rethink of the basic physics of how these particles interact with Jupiter's atmosphere. Amazing. What's next then? How do they solve this puzzle?
Well, several things. They need to dig much deeper into comparing the Webb and Hubble data, trying to model exactly what kind of particle shower could create that infrared bright UV faint signature. They also want to understand what these rapid changes and this weird particle energy distribution mean for Jupiter's overall atmospheric heating, its chemistry, and even its whole magnetosphere, the magnetic environment around it.
And I gather they're bringing in data from another mission, too.
Yes, absolutely. They plan to compare these Webb and Hubble results with data from NASA's Juno spacecraft. Juno is actually orbiting Jupiter right now, flying much closer, measuring the magnetic fields and particles directly. That ground truth, or rather Jupiter truth, could be crucial for figuring out where these low-energy particles are coming from and why they produce that bright spot for Webb.
It really highlights how these different tools, Webb, Hubble, Juno, all work together, and it underscores the power of Webb, doesn't it?
Immensely. Webb is, well, it's the most advanced space observatory ever launched. We often hear about it looking at distant galaxies and exoplanets. But these Jupiter results show its incredible power for studying our own cosmic neighborhood, too. It's a testament to what NASA, ESA, and the Canadian Space Agency can achieve together.
Okay, so let's wrap this up. What are the main things we should take away from this deep dive on Jupiter's flashing auroras?
I'd say 3 key things. 1, Jupiter's auroras are vastly more powerful and complex than Earth's, fueled by both the Sun and its moon Io. 2, Webb's infrared view revealed they're surprisingly dynamic, flickering much faster than expected, tracked via that H3+ molecule. And 3, there's this fascinating mystery where the brightest infrared spots seen by Webb don't show up in Hubble's ultraviolet view, challenging our models and maybe pointing to unexpected behavior involving low-energy particles.
Definitely some big aha moments, and clearly some big questions still remain. It really shows science in action, finding the unexpected.
It does. And it makes you think, doesn't it? About this incredibly complex interplay, magnetic fields, volcanoes on a moon, solar wind, all creating these light shows. It really poses the question, what other fundamental processes, these intricate connections, might we be missing or misunderstanding, not just at Jupiter, but elsewhere in the universe? It's a reminder that there's always more to discover.